given the trends as a starter, I will then actually talk about very innovative technology that ZeroPoint has developed over the years that is there to mitigate some of the bottlenecks that are creeping up in memory systems. So as a computer architect, I have to say something about Moore's law these days, right? So what we see here is basically the miniaturization in business, right, of CMOS technology. And as Gordon Moore pointed out, with each new technology node, about every 2 years, we would expect twice as many transistors on a die. But as we can see from, let me see if I can get this working, yes. As we can see what has happened over the last years, in fact, these 2 years has become 3 years and 4 years. And the current expectation is that 7 nanometer, that's it, and then that's kind of very likely the end of transistor scaling. That's where we will end up. So this diagram was published a few years back with all these great trends since the first microprocessor in the beginning of the 70s. Of course, transistor scaling in a logarithmic, it's exponential because here it's a logarithmic scale, and single thread performance, which tapered off, and which was actually the reason for this annual event, Multicore Day, right? So we started with the Multicore era, but in fact, all this is now gonna taper off. And so being a computer architect, there are all reasons to think about new ways, drastically new ways, I would say, how to scale up system performance moving forward. And this is not only an issue for computer architects, I would say, because all across the stack we have to look for how we can push up performance. And there are good news, in fact, because what has happened over the years is that we have had the luxury as software developers to not care much about how efficient code we write, because Moore's law has translated into an exponential performance growth, which has been eaten up by software, essentially. So there's a lot of optimizations all across the stack to happen. But now I'm going to focus more on the hardware part of the stack, right? What we also see happening is this growth in data. So as was pointed out in one of the talks earlier today, is that 90% of the data today was created in the last 2 years. And this puts a lot of pressure on a computer system in terms of measuring up to memory capacity and bandwidth. And there is one very old, cute, I would say, a rule of thumb, which is called actually Amdahl's rule of thumb. It's not the Amdahl's law, right? It's the Amdahl's rule of thumb, which basically says that in terms of memory capacity, you need approximately 1 byte per flop per second, right? And given today, you know, when a small compute chip can deliver, you know, like gigaflop per second, then that translates into gigabytes. It has been a fairly accurate trend to follow. And the same goes, there's a corresponding one to memory bandwidth. So memory bandwidth and memory capacity, those are very important resources as we move forward, right? And that's what I like to talk about. Now, with the end of Moore's law, or as we are creeping closer, what happens is that also DDR memory price is going up, as we can see in this diagram. So the memory system, subsystem becomes increasingly more expensive as we move forward. So technologies that can reduce the cost of memory is starting to be very, very important. Another thing is actually, again, connected to this Amdahl's rule of thumb, is that If we look at just iPhones, so the amount of memory that you put in these has increased, and it has to do with that the compute platform in a smartphone, the compute platform, the performance of the compute platform has gone up from generation to generation. So there is all needs to look at techniques that can address these cost increase in memory. Okay. But there are good news also moving forward. So one interesting thing, well, so even if DRAM technology, there are difficulties to scale that, there are actually other technologies coming up, and that's what is referred to as non-volatile memory. So up until very recently, I mean, we have had DRAM basically that operates at latency of about 10 times slower than the a few tenths of times of the process performance. Then on the other hand, there is a huge speed gap to storage, right? Where the latency is substantially higher. And so we build systems to basically tolerate the latency to the DRAM, and we have been fairly good at that, I would say. And then on the other hand, we rely on fairly old and legacy-oriented operating system virtual memory management that deals with context switching when we have to, when the system has to interact with the storage. What is creeping up now is this non-volatile memory, which actually performance-wise is a little bit closer to DRAM than to storage. And this is indeed a very interesting point in time, because what happens is that the boundary between the memory system and storage is starting to get blurred, right? So we need to rethink, you know, how we write how we architect the whole memory system, including storage. So there are examples of upcoming technologies, but what is certainly closest to deployment is the 3DX point, right, that you probably have heard from. And this reminded me about a paper we wrote more than 10 years ago, in fact, that I'm going to go back to. We looked into actually the opportunities of thinking about main memory as being you could say a memory hierarchy in itself. So what we want to really build is a large main memory that also has large low cost and low latency memory system. That's the goal of any memory hierarchy, I would say. And that is achievable by actually having classical DRAM as a cache for the MVM. And just to take an excerpt of a paper we wrote so many years ago, where we actually showed that you could actually achieve this big, huge main memory, which is also fast and low cost, by actually making the second level, M2 here, 10 times slower. If you have a third of it, a third of the entire capacity here is DRAM and 2/3 is, for example, Optane. That we showed across a large set of benchmarks, including server workloads, etc. And in fact, to explain this diagram here, it's a little bit hard to see all the numbers, but I'm going to navigate through it with you. So on the y-axis here, we have basically the slowdown, how much we slow down, in this case, SAP, in percent. So it's, actually I have to creep close to myself and take my glasses, but it's 10% here, 15% here, and 20% here. And then what we have along these axes here is essentially the percentage of the total capacity that sits in M1. So for example, we have 40% here, 20% here. And then here we have basically the latency to M2. So if we take an example here, we make the latency to M2 1 microsecond, which would be pretty much 3D X-point. 3D X-point is probably a little bit faster. Then we can see that we could actually afford to, if we are here, if we, for example, take 30%, it results in less than 5% of performance degradation, which would be a fine thing to, I think less than 5%, if you can guarantee less than 5% performance degradation for a substantial reduction in cost, that would be really interesting. So what's the implication of this? Well, you could use it for Optane or something like that. You can also think about having data compressed in M2 so that you can gain capacity that way. So there are a lot of different applications of this multi-level main memory hierarchy. Okay, so let me now switch gear to what zero-point technologies has developed over the years. So we actually thought, still when this project was at Chalmers in my research group, we had seen over the years that there is a lot of data in memory that is, there's a lot of value duplication happening in memory, okay? So if it was possible to really do compression and decompression fast, because you need to decompress the data before you can, well, absolutely, it's not fundamentally needed, but that would be a first big step to be able to decompress data so fast, so you can obviously do calculations on it, right? It could also help, so that would actually enable a lot of memory expansion, increasing the capacity. The second point is also that you could bring in data if you can bring in data in compressed form on the chip, then you can gain, buy yourself higher effective memory bandwidth. And the third point, since you reduce the traffic, then you can also lower the power consumption. So these are all, you know, really important benefits that can translate into huge values, okay? So in 2010, Angelos Hierarchies came to Chalmers for his PhD studies, and we had a lot of fun over the years. In 2015, he graduated, and basically then we started zero-point technologies together. And has been a really fun journey. I'm going to tell you a little bit about what we did. We got venture funding in the first year, and now we are a team of about 10 people. Not all are working full-time, but most of these 10 people are working full-time with expertise in computer architecture, of course, in FPGA ASIC design, and also in software development, as I will comment on in a few seconds. By the way, we are hiring, so couldn't omit to say that. So, first of all, what's the value here? Well, I've already said that. We can increase memory capacity and effective memory bandwidth, and I'm going to tell you how we do that, actually. This can also be used, of course, on the chip to, so for example, the last level cache consumes pretty much half of all the transistors on a chip. So, of course, there's an interest to also do compression in the caches because then you can increase the utilization of on-chip resources. But I'm not going to talk too much about that. So here is what how we actually have packaged our technology. It's indeed an IP block that sits basically close to the memory controller, right? And then it interfaces on the other side to the processor cache subsystem. And what this block includes is unique patented compression technology. So we have done a lot of innovations on the algorithm side as well as on the implementation side, because if you don't easily put, a big brick between the memory and the processor, because that will fall on the critical memory access path and may lead to performance loss. Okay, but I will get back to that, how we actually avoid being trouble for the performance. So there are very highly tuned compression decompression accelerators, and what is unique about this is that it's an entropy-based compression technique that actually does data analysis and create encodings that are geared towards the distribution of data in the memory. Okay. And what we set out from the very beginning is to package this in a way, of course, to not have to do any modifications to the virtual memory management. So this is totally transparent to the operating system. And the trouble you have with doing memory compression, it's actually not a trivial problem to solve, because now suddenly pages have different sizes and you have to manage, fragmentation and stuff like that. And why the operating system thinks that everything is in order with fixed size pages, and it's not, right? So we actually have our own management of the compressed address space, which actually is hidden totally from the operating system. And right now what we managed to do is actually to double the capacity of the DRAM and also the memory bandwidth. It's of course data dependent, so it varies from application to application. Some applications can enjoy much higher compression ratios, whereas others enjoy a lower degree of compression. But all across the board, that's where we are, and we are still kind of innovating. So this is ongoing work. Novel aspects of the technology, I said a few words about that it's entropy-based compression. So we do data sampling, basically in the background, check the nature of the data and value distribution. And then we have developed a whole bag of different compression algorithms that are specially geared to certain data types like floating point data, etc. And so in fact, here is how we interface to the operating system. We do that through device driver, proprietary device driver, where we have all the magic that is going on to maximize the utilization of the memory that we free up. You might have heard about SEDRAM. So all operating systems today, they have a swap space where they compress basically data that ends up there. And in comparison with that, the problem with that is that you can only afford to have like a small fraction of the physical memory devoted to that page cache, because otherwise system performance will suffer. So you can only, let's say 20%, you can only then, with a factor of 2 in compression, get 20% more memory. That's essentially it. Whereas what we do is actually we compress everything in the memory, right? And so that's why we build substantially higher value than what is out there, okay? Right. And here's some data I would like to finish with. So this is basically the compression ratios as they happen for Spec 2017 benchmarks. And as you can see, it varies all across the board. But on average, we are at 2.2 with a bare compression ratio. Whereas if we take the fragmentation, taking our proprietary memory management algorithms into account, we end up with 2, as I said, a compression factor of 2. Question is, how does this translate into higher performance? So this is an experiment we did also with Spec 2017 applications to basically make the data set twice as big as the physical memory, okay? And normally if you would run that on a system, then for memory intensive benchmarks, then the system would trash. And so what we see here is in fact the performance improvement if we add our IP block to a system with a certain amount of memory, run applications with twice the size of the data set, then, or footprint as it is also called, then we can see that some of these applications that happen to be memory intensive, they actually enjoy a substantial increase in performance that all across the board leads to 30% performance improvement. So that's one way of using our technology to actually buy higher performance, but you could also play the other trick of actually building a less costly system by being able to run it with less memory. Right. Here is an interesting, so I said it's not a no-brainer to just put an IP block right on the critical memory access path between the processor and the memory, because pair, I often get the question, pair, how much does that hurt performance? Then my pushback is it doesn't hurt performance, it helps performance. How can that happen? Well, in fact, why it can happen is that it has to do with the fact that we can bring in, when we request a memory block from memory, since it's compressed, you can fit, you can be lucky and fetch several blocks in one go, right? So because of that, you actually, that will of course lead to less traffic, lower power consumption, but very importantly, shorter latency too, because you can, those blocks that come in the same transaction, you can put them in what we call a prefetch buffer, and then you can, if there is high spatial locality in the access pattern, then you can benefit from it. And that's what we can see here, that you get actually an increase in performance. So all across the board for these benchmarks, we get some slight decrease in memory access time, which is pretty cool. Of course, in some cases, you cannot, if you have pointer chasing and things like that, then you might suffer a little bit, but it's just a few percent we have seen that we suffer from, that we add latency on the critical memory access path. All right, so where we are right now with this technology is that we have RTL code ready for the IP block, and we are talking to quite a lot of big companies, I would say, that have got interest in this. One very important point is, of course, the size. If we were to sell an IP block that, well, it became a trade-off with a number of cores, for example, then, well, it's going to be a hard sell. So we have really put a lot of effort to get down in size with this IP block, and managed pretty well. It doesn't scare off potential customers with the size. Okay, so that was pretty much my talk. I did it in pretty much 28 minutes. There should be some time for questions. Thank you.